Hey everybody, welcome to chapter 7. We're talking about probability. Now, probability is a really foundational concept in statistics, although we don't really do a whole lot of direct probabilities like we're going to be doing some of today. But probability is really, really valuable in hypothesis testing. And so let's just say, let's take an example. I think that listening to good music increases your happiness. Okay, so what I'm going to do is then find groups of people and maybe assign one of them to not listen to good music and assign another one to listen to good music. And then I'm going to measure their happiness level so I can compare those things, right? And basically what's going to happen is I'm going to find an average happiness for each of those groups. And in order to compare them, I'm basically going to say, well, what is the likelihood? What is the probability that listening to good music actually does increase happiness significantly? And if I find a really high happiness average, what's the likelihood that I would find such a high happiness in that group that listened to good music if music really had nothing to do with happiness? And so this is all about hypothesis testing. What I just described will make a lot more sense as we talk through the next few chapters and actually get to inferential statistics. But all that to say is probability is a really important concept because it's how we decide as researchers whether something has an effect on something else. So let's dive in. As a little bit of a roadmap for what we're doing this chapter, mostly today we're going to be talking about discrete probabilities and the addition and multiplication rule, and then later on we'll talk more about continuous probability and yeah, get to some cool stuff. So let's go ahead. So here's a question for you. Do you believe that gambling is a good investment strategy? Hopefully you said false on this one, right? And there's a good reason for that. It's because that casinos and companies who create lotteries and scratch tickets and those kinds of things, they know that the probability is in their favor, that they are going to win most of the time. So of course, some people win some money sometimes at casinos and scratch tickets and all that kind of stuff. But casinos and lottery companies specifically set it up so that they're going to make more money than they're giving out, right? They're a business, so they're going to make more money than they're giving out because the probability is in their favor. And just kind of a funny anecdote, a lot of famous mathematicians have sort of like a probability era that they go through where they get really interested for a year or two in probability. Einstein was no exception. And he calculated the probability of winning in roulette, which is very slim, especially if you're betting up for one particular number. He says you have a better probability of winning at roulette by punching the attendant and stealing the money as opposed to actually trying to gamble. Okay, so not a great investment strategy. So we're going to get into a little bit of math here. We got to talk about probability, and probability is basically the likelihood that an event will occur out of a certain number of events. And so what you see here is two different kinds of ways of going about approaching probability. The first one is called a priori, which means before. So this is armchair philosophy. This is we're thinking about, well, what would the likelihood of an event happening? If I flip a coin, but I'm not even going to flip the coin. I'm just thinking about what would happen if I did flip a coin. What's the probability that I'm going to get a heads? Or what's the probability I'm going to get a tails? I don't even have a coin on me, right? But you can do the thought experiment in your head. That's a priori, before the event actually occurs. And what you see here is a little p for probability, and in parentheses a. This is probability of an event A. An event, it would be something like getting a heads on a flipping a coin, or when we're talking about if you've had, if you played poker or had a 52 card playing deck, you played Go Fish and things like that. Let's take what's the probability of pulling a red card out of a deck, right? So in a normal 52 card playing deck, there's 4 different suits. 2 of them are black colored suits, 2 of them are red colored suits. Each suit has 13 cards in it. Okay, 52 cards. Each of the 4 suits has 13 cards. So that means that if you were to think about what's the probability of pulling a red card out, well, there's 2 suits. Each of those is 13 cards. So that's 26 cards out of a 52 card deck. So the probability of pulling a red card at random out of the deck should be 26 divided by 52. So the number of events classifiable as A, which is pulling a red card, divided by the total number of events. That's the total number of cards. Okay, so that should be 26 over 52, which is 0.5. The probability of pulling a red card is 0.5, which means 50%, right? So that's all a priori. I didn't even pull the card out. I don't even have a deck in front of me, right? But a posteriori, which translates to after the fact, well, now it's basically the same thing, except for you're actually doing the exercise. So if you had a 52 card playing deck in front of you and you just at random start pulling cards out of the deck, then you see what it is, and then you put that card back in the deck, so you're always pulling 1 card out of 52 cards, and then you actually count, well, what was the actual number of times that I pulled a red card out of that deck compared to the total number of times I tried to pull a card out of the deck, right? So you might end up, and we would do this hundreds of times, thousands of times, maybe millions of times, okay? If you only did it a few times, what you would find is that, well, the probability probably wasn't exactly 0.5 like we would have estimated a priori. But if you actually do it enough times, let's say a few thousand times, the number of times that you pull a red card out of the deck is going to be much, much, much closer to 0.5, to half the total times. Okay. And casinos know this, right? So it's like, yeah, sometimes some people are going to get lucky and they're going to win a bunch of money. But when you are thinking about an event happening thousands and thousands and thousands and thousands of times, after a lot of different events, what you find, typically speaking, is that the probability a posteriori starts to resemble more and more and more the actual a priori probability that we can calculate beforehand. Now, in this class, we're mostly going to work with a priori calculations of probability. So let's try to do some of that stuff. Now, probabilities are always between 0, which means there is no possible chance that an event will occur. It is actually impossible for that event to occur. That would be a probability of 0, all the way up to 1.0, which is 100% chance that the event will occur. So if I have, a trick coin and both of the sides of the coin are both heads, then the probability of getting a heads when I flip it is 1. There's a 100% chance that I'll get a heads, right? So in a standard deck of cards, what is the probability that you will pull a diamond card from the deck? And remember, there's 4 suits: clubs, spades, diamonds, hearts. Each of those suits has 13 cards in it. So what is the probability that you will pull a diamond card from the deck at random? Well, the probability should be 13 divided by 52. There's 13 diamond cards out of the 52 card deck. And what you'll find if you do that is it will result in a probability of 0.25. You have a 25% chance of pulling a diamond from the deck. So let's get a little bit more complicated now, and we're going to go over something called the addition rule in probability. So if you have one single event, you're going to pull 1 card out of the deck, but you're interested in whether that card is going to be either, let's say, a red card or a 5. Well, now you have to think, about a few different things going on at the same time. Okay, so the probability of A or B, the probability of pulling a card that's either a red card or a 5 is going to be equal to the probability of each of those things happening independently, probability of pulling a red plus probability of pulling a 5, but then you have to subtract what is the probability of pulling a single card that is both red and a 5. Okay, so there's this idea of mutual exclusivity. If two events are mutually exclusive, it means they cannot happen at the same time. It's impossible for them to happen at the same time. So that would be something like if I said, what's the probability of pulling one card that is either red or black? Well, you can't pull a single card that's red and black, right? It's either going to be red or black. So in that case, it would just be probability of it being a red plus the probability of it being a black. But then that last part, the probability of it being both of those things at the same time, that would just be 0 because it's impossible, right? So those things are mutually exclusive, pulling a single card that's red and black. But in our first example, pulling a single card that is red or a 5, those things are not mutually exclusive. Okay, because you could pull a card that is both red and a 5. A red 5 would be a 5 of diamonds or a 5 of hearts. So let's walk through how you would actually calculate that in this example. All right, so now we're talking about the probability of pulling a red card or a 5. And so you can think about this, and I even encourage you to pause the video and try it on your own if you are courageous enough. So here's how you would approach this. Okay, so the probability of obtaining a red card or a 5. The red card is event A, a 5 would be event B, is equal to the probability of pulling a red card, probability of A, which we already know, right? That's 0.5 because there's 26 red cards out of the 52 card deck. 26 divided by 52 is 0.5, so there's 50% chance. You add the probability of that card being a 5. Each of the 4 suits has a number 5, so there are 4 number 5 cards in the deck. So 4 divided by 52 with some rounding is 0.077. So not quite 8% chance of pulling a 5. But those two things are not mutually exclusive. So you have to also think about subtracting the probability that the card that you pull out is going to be both a red card and a 5. Well, if you think about it, okay, there's 4 5s in the deck. Only 2 of them are red 5s. Again, the 5 of diamonds or the 5 of hearts. So 2 divided by 52 with some rounding is 0.039. And if you add 0.50 and 0.077, the probability of getting a red card plus the probability of getting a 5, and then you subtract out the probability of getting a red 5, you end up with a probability of 0.538. So about a 53.8% chance you will pull a single card from a 52 card deck that is either red or a 5. And it's worth thinking about, like, well, why do you have to subtract out that piece that's both, right? It's the wording of the prompt. If you're talking about using the word or, then you're really interested in those probabilities separately, not the probability of pulling a single card that is both red and 5. So you got to subtract that piece out of it. Now, obviously, if the question was, well, what's the probability of pulling a red card and a 5? A red and a 5. So it's either going to be the 5 of diamonds or the 5 of hearts, right? Well, then you can just do 2 divided by 52, and that gives you 0.039. Now, remember on tests and quizzes and things, okay, in this class, we're going to round the final answer to 2 decimal places, basically for every single number in the entire class, with the exception of one specific kind of number, which is called a p-value. And I'm not talking about these p-values here, so sorry if that's confusing. You will know when I'm talking about p-values. That happens when we're doing hypothesis testing using inferential statistics. These are probability values, but we round everything in this class, the final answer, to 2 decimals. Now, when you're actually calculating all this different stuff, right, you can see that I've rounded to 3 decimal places in some places, which I would recommend. Like when you're actually doing the calculations, you want to use several decimal points and then only round at the very end. Okay, just round the final answer to 2 decimal places. All right, hopefully that makes sense. Let me know if you have any questions about that. Okay, we just talked about this a little while ago, but in a standard deck of cards, what is the probability that you will get a red card or a black card when you pull a single card from the deck? Well, of course, it's going to be 1, right? Like whenever you pull a card, it's either going to be red or black. And those things are mutually exclusive, which means on the previous slide, you would add up the probability of pulling a red card, which is 0.5, plus the probability of pulling a black card, which is also 0.5, and then you wouldn't subtract anything from that because the probability of getting a red and black card is 0, so you don't have to worry about the subtraction part. So 0.5 plus 0.5 is 1. All right, here's another example. In a standard deck of cards, what is the probability that you will get a red card or a face card? A face card is a jack, a queen, or a king. And there are 4 suits, each of which has 3 face cards, so that's 12 face cards. So see if you can figure out the answer to this one. Well, if you were to calculate the probability using the addition rule, you would first say, okay, what's the probability of getting a red card? Well, we already know that's 0.5. What's the probability of pulling a face card? Well, that's going to be 0.23. What is the probability of getting a red card that is also a face card? Now that's going to be 6 divided by 52, which is 0.115. So if you add 0.50 plus 0.23 and you subtract 0.115, you will end up, after some rounding, with an answer of 0.62. You got a 62% chance of pulling a card that is either a red card or a face card. All right, let's talk about the multiplication rule of probability. Now, in the addition rule, we were only thinking about a single event. And what is the probability, the likelihood of a single event? Even if we were thinking about potentially, different factors, like if it's a red card or if it's a 5 or something like that. In the multiplication rule, we are thinking about multiple events. Okay, and in this case, let's just talk about 2 events that happen one after the other. Well, how you calculate the probability depends on if those 2 events are what's called independent, they have nothing to do with each other, or if they're dependent. And then the probability of the second event changes depending on what happened in the first event. Okay, so let's give some examples. With independent events, we're looking for the probability of A and B both happening. That is the probability of the first event times the probability of the second event. And so, for instance, if I pull a card out of a deck and I want to ask, well, what's the probability of getting a 2, and then on the subsequent pull, what's the probability of getting a 5? Well, it depends. if I'm pulling the card out and I'm seeing if it's a 2, if I leave that card out of the deck, now there's only 51 cards left in the deck, right? And so the probability of then also picking a 5 with the second card, well, the chances have changed because now you're just looking at if there's 4 5s, now you're going to divide that by 51 cards instead of 52. So you actually have a little bit better odds if you didn't pick a 5 on the first go. So this is called picking cards with replacement. If there's independent events, that means you pull a card, you see if it's a 2, you put it back in the deck, then you pull another card at random and you see if it's a 5. Okay, so those things are independent. So this is picking cards with a replacement. Another example would be of independent events that do not rely on each other or change the probability depending on what happens the first time around, is it flipping 2 coins in a row. If you flip a coin, the result of the first coin flip doesn't have anything to do. It doesn't influence the second coin flip, right? So those would be independent events. And then you just need to multiply the probability of the first thing happening times the probability of the second thing happening. But there's a different kind of event which could be called dependent events. And here the probability of both A and B happening is now equal to the probability of the first event, A, times the probability of B given A. So that you can see that the B slash A, that slash means given. And so it's the probability of event B given that we saw A already occurred. Okay, so this would be, again, the example is you pick a card out of a deck, you see if it's a 2, you do not put it back. Now there's only 51 cards in the deck, so you pick another one and see if it's a 5. Well, the probability has changed. Okay. Another example of a dependent event, just sort of in the world, would be if you ask, you're a researcher studying relationship satisfaction amongst monogamous couples, and so you ask the first partner, hey, what is your relationship satisfaction? And they give you, on a scale of 1 to 10, and they give you an answer. Well, then you ask the second partner, what is your relationship satisfaction on a scale of 1 to 10? Those things are going to be dependent on each other because typically speaking, right, like your partner's satisfaction in the relationship is also going to influence your satisfaction in the relationship. So those things would be dependent. So let's get some examples with both of these. So let's look at independent events first. Let's talk about what is the probability of pulling a red card, then you put it back, and then you pull a spade. Okay, so because this is with replacement, these events are independent of each other because it's always going to be a 52 card deck and you're pulling a card at random both times, right? So the first time when you want to know what's the probability of pulling a red card, well, we already know pulling a red card has a probability of 0.5. Then you put it back, and then you pull another card. And what is the probability now of pulling a spade? Well, a spade, there's 13 spades. You divide that by 52, you get 0.25. So now you multiply the probability of pulling a red card and putting it back and the probability of pulling a spade, because you're interested in what is the probability that I first pull a red card, then pull a spade. Okay, exactly how that is in order and exactly those two things. Multiply those two things together, 0.5 and 0.25, you get 0.125, but we'll round it up. So that's going to be 0.13. So you have a 13% chance of first pulling a card that is a red card, putting it back, and pulling a card that is a spade. Here's another example of independent events. What is the probability of flipping a coin twice and getting heads on both flips? Well, the first time you flip the coin, you've got a 50-50 chance, right? 0.50 of getting a heads. And that does not influence what the coin flip will be the second time you flip it. So you just multiply the probability of getting heads on the first flip is 0.5, and the probability of getting a heads on the second coin flip is 0.5. Multiply 0.5 by 0.5, and you get an ultimate answer of 0.25, or a 25% chance that if you flip a coin twice, both times the result will be a head. Okay, how about for dependent events? All right, so let's try, what is the probability of pulling a red card, not putting it back, and then pulling a spade? All right, so in this case, the probability of B given A is different because there's only 51 cards now. So the probability of A pulling a red card, we already know, is 0.5. Probability of B given A, well, there's 13 spades, but now there's only 51 cards in the deck. So 13 divided by 51 is 0.255. If you multiply the probability of A and the probability of B given A, 0.5 times 0.255, you get 0.127. So your chances have increased a little bit, a tiny amount, because there's fewer cards after the first pull, right? Now, of course, in this class, we're going to round to 0.13, so it's still going to look like 13% chance, even though the probabilities have shifted a little bit. All right, let's get you some practice. So, what is the probability that you will get a red card? You're going to put it back into the deck, and then you're going to draw a queen. Well, since this is with replacement, these events are independent. They don't affect each other. Okay, so you multiply the probability of getting a red card, which is 0.5, times the probability of then getting a queen. There's 4 queens in a deck, so 4 divided by 52 is the probability of pulling a queen, which is 0.0769. So 0.5 times 0.0769, excuse me, you end up with a total probability of about 0.038, and you're going to round that to 0.04. So there's about a 4% chance that you will first draw a red card, put it back in the deck, and then draw a queen. All right, how about this one? What is the probability that you will get a jack when pulling the first card out of a deck? You do not replace that card. And then what is the probability of pulling a club on the second card? So first, to get a jack, you're talking about 4 cards out of 52. 4 divided by 52 is 0.0769. Then you don't put the card back. So now the probability is going to be out of 51 cards for pulling a club. So that's 13 divided by 51, 0.255. You multiply 0.0769 and 0.255, and the final answer is going to be about 0.02, 2% chance. Now, some of you have probably been wondering, well, when we have these multiple events in a row, well, what happens if, for instance, on the first card draw, you pulled a club, right? And so whether you get a jack or not, if you pull a club on the first pull and then don't replace it, then when you try to draw a club on the second pull, that's going to change the odds, right? And remember, what we're just talking about and describing is pulling the cards and actually doing that as an experiment. That would be called a posteriori. That would be actually trying to figure out what are the probabilities as we're doing them. But most of the time, and especially in this class, oftentimes, we're using a priori before you actually do any of the actual pulling of the cards, flipping of the coins, those kinds of things. What are the probabilities without knowing what you actually get, okay? And so there's a bit of a difference there. So when in doubt, we're just going to go with the a priori. We don't actually know what card we pull the first time around, but we can guess just in general, what would be the probability of getting a jack and then a club without worrying about what card you actually pull, if that makes sense. All right, that's it for this video. I'll see you in the next one.